All right, so the last section of notes here is on acids, bases, and pH. So if you take a look at these things here, they all are acids. And these are some of the different acids that are found in these different items. They're all common household items, and they all have acid in them. So let's talk about exactly what an acid is. An acid is defined as a substance which forms a lot of H plus ions in solution with water. And we're going to be talking a lot about this H plus ion thing. Okay, it's called the hydronium ion, but I'll probably call it the H plus just because that's how it's written. Acids have the characteristic of tasting sour. They conduct electricity when dissolved in water, so that makes them what we call an electrolyte. They react with bases to form water and something called a salt, which is what we call a neutralization reaction. They change indicator colors, and compared to water, they have more H plus. Now, acids have a partner, and that is the base. Bases have a different definition. They form a lot of hydroxide or OH minus ions in water. You can also think of this as very few H plus, which sometimes people find helpful. Bases have different characteristics, but they also have some that are the same. They, instead of having a sour taste, they have a bitter taste. If you come in contact with your skin, they have a slippery or soapy feeling. They are caustic, in other words, they cause burns. Now, they are alike with acids in that they react in a neutralization reaction, so they can react to neutral. They also are electrolytes because they conduct electricity in water. The last thing that they share in common is that they change indicator colors. Now, they change them differently, but they do change the indicator colors. Now, acids have more H+, bases have less H+ than water. Now, both of these things we associate with the term pH. So let's talk a little bit about what pH is. pH is a quantitative, in other words, we assign a numeric quantity to the strength of the acid or the strength of the base. What it is actually measuring, though, is the amount of H+, which is the acid ion in solution. So that's why I was referring to that H+ when we were talking about both acids and bases, because pH relates to that. Now, in your notes, you're going to want to sketch this number scale. Okay, this is the pH scale. Low end is 0, although we have had some ones that are lower than that, and the upper end for most things is 14, although we do have some areas that are higher than that. 7 is important, it's in the middle, that is neutral. Neutral means it's neither an acid nor a base. On this side, we are acidic, and above 7, we are basic. Now, the way you have to think of this, though, is in terms of when you're measuring the strength of an acid or strength of the base, it's how far is it away from neutral. So in the basic range, that's easier because the higher the number, the stronger the base. But when you're in the acidic level, it's different, and this is tricky. You have to really keep this or get this down. The further I move away from 7, the lower my number gets. So you have to really, really be careful there. The lower the number, the stronger the acid. We're not going to worry about that. All right, so why is water neutral? Well, if you think about water, okay, water is H2O. So let me just write that up here. It is H2O. And it can actually split apart. If I write it like this, I still have H2O. And I can split that apart into this and this. We have an acid ion and we have a base ion. So water is actually made up of each of the ions that make up acids and bases. So if we looked at a container of water, what I would actually see, if I could look close enough, is that I have H pluses and hydroxide, OH minus, floating around in there. But if I look, I have 1, 2, 3, 4, 5 H pluses and 1, 2, 3, 4, 5 hydroxides. So the number of H plus is equal to the number of OH, so water is neutral. So we're going to kind of go through some things here with acids and bases and then come back to this illustration. So remember, between pH of 1 and 7, it is acidic. That means we have a lot of H plus ions in water that are created by acids. Now I want you to put a star or something next to this next bullet point because it's very important. The lower the pH, the stronger the acid. So now let's take a look at actually what's happening. So we're going to start with our container again, and we're going to start with just water in there. So the amount of H plus and the amount of OH minus is the same. But I'm going to add HCl, and my HCl is going to split apart. I'm going to add that into the solution. Remember, that is our acid ion. Now the Cl ends up in here too, but it doesn't really affect our pH. So I'm adding more H plus. So now my amount of H plus is greater than my amount of hydroxide, so my solution is acidic. I still have hydroxide ions in there, but they're overpowered by the H plus. It wins. It's like a tug of war almost. Now if I look at the other one, with bases between 7 and 14 is basic or alkaline, and that means very few H plus ions in the water. These are created by bases, and this one is the easy one. The higher pH, the stronger the base. So again, let's go back to the illustration. We're going to start with our water again. So I have equal amounts of H plus and OH minus, and this time I'm going to add something that's a base, sodium hydroxide. So it has that OH there. Now again, the sodium goes in, but it doesn't really matter. But what I'm changing in my container is the amount of OH minus. So now the amount of H plus is less than the amount of OH minus, so the hydroxide wins, which is the base ion, so the solution is basic. So we eat things, and a lot of things that we come into contact with in our daily lives are acids or bases. But we talked about with enzymes how pH is important. So how are we able to consume these things like grapefruit or whatever and not change the pH and therefore denature our enzymes? Well, that's because of some handy-dandy things called buffers. Buffers are defined as weak acids or bases that prevent sudden changes in pH. And in our bodies, we have blood. Blood is actually a buffer, so it helps us to bring in acids and bases into our systems, but not change the pH of our bodies that much. Seawater is important for a lot of single-celled living organisms, and it does the exact same thing. So buffers are important for living organisms because we need homeostasis to be maintained. Without enzymes, we can't do that. Now, when we looked at characteristics of acids and bases, we also had talked about indicators. And acids and bases are capable of changing indicators. And indicators are any substance that changes color in the presence of an acid or a base. And the color change will happen at different pH levels depending on which indicator we use. Some common indicators include things like litmus paper. Litmus paper will stay red or turn red in an acid, blue in a base. Phenolphthalein is a liquid, and if you drop it in, it'll stay colorless in an acid, but it will turn bright magenta pink in a base. And pH paper. Now pH paper is going to change color no matter what. Basically, you dip it into whatever you're testing and then match up the color that the paper turns with the scale on the side of the bottle. Nature also has some indicators though. For example, beet juice. If I take beet juice and I expose it to a base, it will actually turn purple. Red cabbage juice is another one. It'll turn red in an acid, neutral in purple, and then a greenish yellow in a base. The last one is a hydrangea, and this is a flower that I know a lot of you have outside your houses or where you live, and the flowers there will actually be blue if the plant is exposed to acidic soil and pink if it's in the basic soil. So you can actually change the color of your flowers on these trees by changing the pH of the soil that they're in. And yes, you can get both color flowers on the exact same bush. Now the other thing that they had in common was the fact that they undergo neutralization. So let's take a look at neutralization here. This is what occurs when an acid and a base react with each other. Basically, the H plus of the acid combines with the hydroxide of the base to form water, and the leftover parts combine to form a salt. And when we talk about salt in chemistry, we're not always talking about the salt that you sprinkle on your French fries, but it's similar. Now, what I did here on this example reaction is I actually made the H plus, the acid ion blue, and the hydroxide, the base ion, red. And you can see here that it combines to form water, and then the leftover black piece is combined to form our salt. When this type of reaction happens, the properties of the acid and base disappear, including their respective pHs. They go, and I want you to put this in here, they go to neutral, so it turns to 7, because 7 is neither an acid nor a base.